In this video, we'll explore spatial proportional reasoning. In Math 8, your child looked for and made use of relationships between quantities to solve problems in a variety of contexts. In Math 9, your child will continue to develop proportional reasoning through situations that involve 2D shapes, for example, scale diagram or similar triangle problems. We'll begin by exploring a problem to deepen your understanding of proportionality. Consider this image. Suppose it represents a photo that you wish to have enlarged. Which of these photos look the same as the original? Labeling the photos will make it easier for us to talk about them. Don't worry about making an incorrect choice. You'll have an opportunity to revise your thinking later on. How confident are you? The dimensions of the photos might be helpful information to have. The original photo has a length of 4 inches and a width of 3 inches. The dimensions of the other photos are shown here. Revisit your answer to this question. Do these numbers confirm your earlier choices, or do they cause you to change your mind? Press pause and proceed when you have convinced yourself that you have correctly identified the look-alike photos. Photo B is a true enlargement of the original photo. You may have spotted some doubling. Let's take a closer look. We can write a proportion to express the relationship. A proportion is an equation that says that two ratios or rates are equivalent. Notice that the fraction on the left represents the dimensions of the original photo, and the fraction on the right represents the dimensions of photo B. Also notice that the numerators represent the lengths, and the denominators represent the widths. This proportion says that the ratio of length to width is the same for the two photos. When writing a proportion, it's important to think about what each number represents. Doubling 4, the length of the original photo, gives 8, the length of photo B. Similarly, doubling 3, the width of the original photo, gives 6, the width of photo B. These two multipliers, or scale factors, are the same. This means that photo B is an enlargement of the original photo. You may have also noticed a relationship between length and width within each photo. The width is 3/4, or 0.75, times the length. We could have written a different proportion. Here, the fraction on the left represents the lengths and the fraction on the right represents the widths. The numerators represent the dimensions of the original photo, and the denominators represent the dimensions of photo B. This proportion says that, whether we're looking at length or width, the ratio of original to photo B remains the same. Here, together, are the two proportions. Notice that we can see the same multipliers as before. Let's return to the collection of photos. There's another photo that looks the same as the original. Photo C. Each fraction represents the ratio of length to width, the original on the left and photo C on the right. Notice that the scale factor across both length and width is the same, 1 1/2 or 1.5. Also, the relationship between width and length within each photo remains the same. 4 1/2 is 3/4 of 6, as is 3 of 4. Once again, we could have written a different proportion, but the underlying relationships between the measurements do not change. Let's look at one more photo. Is photo D an enlargement of the original photo? Intuitively, it doesn't look like it is. It looks like it has been stretched more horizontally than it has vertically. The numbers can convince us and determine close calls. Notice that 8, the length of photo D, is double 4, the length of the original photo. However, the width is multiplied not by 2, but by 1 1/3, or about 1.33. The photos are not similar. Imagine that you wish to have the photo enlarged to the size of a poster. Suppose the width of that poster is 48 inches. How long would the poster be? The ratio of length to width is the same in the original photo as it is in the poster. X represents an unknown value, the length of the poster. This information can be organized in a table of equivalent ratios. Notice that multiplying 3 by 16 gives 48. Applying the same scale factor to 4 gives X a value of 64. We can use the table of equivalent ratios to get the same answer in different ways. For example, we might divide both 4 and 3 by 3. This gives us a width of 1. And 1 can be scaled up to 48 by multiplying by 48. Or we might double the dimensions of the original photo, which gives us a width of 6 inches. And to get to the target width of 48 inches, we must multiply 6 by 8. This strategy involves multiplying twice, but some students might find multiplying by 2, then 8, friendlier than multiplying by 16. Let's apply our understanding of proportional reasoning to some questions from the textbook. Calculate the actual size given the scale and the length on a scale model. Give your answer in millimeters. 3.6 centimeters on a 1 to 28 scale model. The scale of 1 to 28 means that 1 centimeter on the model represents 28 centimeters as an actual size. Multiplying the length on the model by 28 gives us the actual length in centimeters. 100.8 centimeters is equivalent to 1008 millimeters. Two ladders are leaned against a wall so that they make the same angle with the ground. The 10-foot ladder reaches 8 feet up the wall. How much further up the wall does the 18-foot ladder reach? This problem involves two nested triangles. The angle formed by the wall and the ground is a right angle. The question states that the two ladders make the same angle with the ground. This means that the two ladders also make the same angle with the wall, since the sum of the angles in any triangle is always the same. Because their corresponding angles are equal, the two triangles are similar, and the lengths of their corresponding sides must be proportional. It will be helpful to pull them apart and draw them separately. Again, we can begin by writing a proportion. This proportion says that the ratio of ladder length to height of the wall is the same no matter which ladder. To make 18 from 10, we multiply 10 by 1.8. Applying the same scale factor to 8 gives a height of 14.4 feet. Once more, we could write a different proportion. This proportion says that the ratios of length to length and height to height are the same for the two ladders. Notice that the question asks not how far up the wall the 18-foot ladder reaches, but how much further up the wall it reaches. To answer this, we subtract to find the difference between the two heights. In this question, we'll dive deeper into similar triangles. To show that the two triangles, triangle AEB and triangle CED, are similar, we can show that their corresponding angles are equal. The question states that angle A is equal to angle C. The angles at E are equal. They are opposite two intersecting lines. Angles B and D must be equal because the sum of the angles in any triangle is 180 degrees. We can say that triangle AEB is similar to triangle CED. Side AE, labeled lowercase b, corresponds to side CE. Side AB corresponds to side CD. The corresponding sides of similar triangles are proportional. The scale factor between the two triangles is 0.8. Applying this to the numerator gives a value of 3.52 for side B. Let's look at a common mistake that students make when determining an unknown side in similar triangles. Suppose that a student identifies 15 and 30 as the lengths of two corresponding sides. Then they match x with 12. However, x does not correspond to 12. Visualizing the rotation and reflection of one of the triangles makes this easier to see. X, the shortest side in the larger triangle, corresponds to 9, the shortest side in the smaller triangle. This video addresses several learning standards in the Mathematics 9 curriculum. In content, we looked at spatial proportional reasoning. Several curricular competencies may emerge as your child learns this content in their classroom. In this video, we used reasoning to explore and apply the mathematical ideas of proportionality, scale, and similarity. We did this when we reasoned to develop strategies for determining unknown values. Further, we developed an understanding of these concepts through problem solving when we solved the problem of identifying which photos looked the same.